Hello, my name is Andres Horta, and today I'll be talking about ATP synthesis and F-ATPase. So first, I would like to talk about the complex, and that's what this slide will talk about. So we have learned that the electron transport chain creates a proton gradient across the inner membrane through the transfer of electrons, and we can begin to learn how ATP synthase works by looking at it. So here we have the N side, which is the side that would have all the electrons. And in the inner membrane space, we would have the P side, which would have protons. And across this inner membrane, we would see the gradient. So the ATP synthase complex uses the proton electrochemical gradient that was established at to synthesize ATP. The ATP synthase has two regions, the F0 region, which is right here, and the F1 region right here. So the F1 region is the catalytic region of the complex, and this is where the formation of ATP occurs. So this consists of the alpha, beta, gamma, epsilon, and delta polypeptide chains. So as you can see here, there's a beta, alpha, epsilon, gamma, and delta subunits. So now to talk a little bit about the F0 region, what we see is that this region contains a proton pump. So this is a mostly hydrophobic region, and as you can see, it is in the hydrophobic region of the lipid bilayer. And this region has the C subunit and the A subunit. So these two unite to combine to make a proton channel that allows the hydrogen ions to flow from the inner membrane space into the membrane. So what we have going on here is we have all the hydrogens from the P side are able to go into the proton channel and into the complex. So what we have here is also the A subunit also unites with two B subunits, the F1 unit. So this connects them together. Another thing that connects them together is the epsilon and gamma subunit from the F1 unit. So when looking at the electron transport chain and what it has done, we see that an NADH molecule has been oxidized and the electrons are transferred into a ubiquinone, which is reduced into a ubiquinol. Now this ubiquinol will go on to complex 3, where it will reduce to cytochrome C, and cytochrome C will go on to complex 4, where it will create two water molecules. And this process and the transfer of electrons through all these complexes will cause 4 protons to pump in the first complex, 4 protons to pump in the third complex, and 2 protons to pump in the fourth complex. So we see that from one NADH molecule, we actually pump 10 protons. And the pump of these protons is actually very important in understanding ATP synthesis because we create what is called the proton gradient. As we can see here, there is the negative charges, which is known as the N side. And across the inner membrane, we also see the positive proton charges. So now that there's this gradient with the protons wanting to come down and the electrons wanting to go up to reach equilibrium, there is a gradient found. And now we can go on to ATP synthase and how it works. So with ATP synthase, we see that the F1 region, which is right here, has the catalytic structure. So this hexamer in the F1 region can bind to ADP and phosphate group, and it can catalyze them to synthesize ATP. So this is all without the use of the F0 region. It can catalyze the synthesis of ATP, and now these subunits will have an ATP. However, it cannot release the ATP without the F0 unit and therefore the proton gradient. So when the proton channel rotates due to the gradient and the protons wanting to come down, we see that the rotation frees up an ATP, releasing it, and allows for a new ADP and phosphate group to bind. And the repetition of this will allow more phosphates to be made, more ATPs to be made from the ADP and phosphate group. Thank you for watching.